In our third episode, we explored how Einstein's groundbreaking work revolutionized physics by challenging and overturning Newtonian ideas. Following this scientific upheaval, attention turned to a new mystery in cosmology. Albert Einstein, along with many other scientists, initially leaned towards the notion of a static universe. To uphold this idea of a stable cosmic configuration, Einstein introduced the cosmological constant into his equations of general relativity. This constant functioned as a repulsive force, working against the gravitational pull between matter. The objective was to maintain the universe in a state of equilibrium, presenting an intriguing and initially favored concept in the scientific community. However, in 1929, Edwin Hubble's observations of distant galaxies revealed that the universe was indeed undergoing expansion. This revelation contradicted Einstein's initial vision of a static universe, leading him to deem the cosmological constant his most significant error. Today's video explores the concept of the expanding universe. To begin, let's delve into the history. The contemporary understanding of an expanding universe originated in the 20th century. If you're interested in how our ancestors picture our universe, you can refer to episode 1. For millennia, humanity gazed upon the night sky, observing the stars and constellations that decorated the cosmic landscape. As early as 1750, astronomers speculated that most visible stars lie within a single disk-like structure resembling a spiral galaxy. This distribution of visible stars that forms a distinct band across the sky is what we recognize as the Milky Way. In the 1800s, Sir William Herschel bolstered the theory by meticulously cataloguing the positions and distances of countless stars. However, the concept of the Milky Way as a distinct disk-shaped structure did not gain widespread acceptance until the early 20th century. Our current cosmological understanding traces back to 1924, when the American astronomer Edwin Hubble fundamentally transformed scientific thinking. At the time, it was firmly believed that our Milky Way galaxy encompassed the entire cosmos. However, through groundbreaking observations, Hubble demonstrated that this was just one of countless galaxies scattered across seeming voids. To support this revelation, Hubble needed to determine the distances to these other galaxies. Unlike nearby stars, galaxies are so distant that they appear fixed in our view. Consequently, Hubble employed indirect methods to measure their distances. The apparent brightness of a star is influenced by two factors: its luminosity, which is how much light it radiates, and its distance from us. For nearby stars, both their apparent brightness and distance can be measured, allowing the calculation of their luminosity. Conversely, if the luminosity of stars in other galaxies were known, their distance could be derived by measuring their apparent brightness. Hubble made a crucial observation. Certain types of stars consistently have the same luminosity when they are close enough for measurement. Therefore, he reasoned that if these stars were found in another galaxy, their luminosity could be assumed to be constant. This insight enabled him to calculate the distance to that galaxy. By applying this method to multiple stars within the same galaxy and consistently obtaining the same distance, Hubble gained confidence in his estimates. Through this approach, Edwin Hubble determined the distances to 9 different galaxies. Today, we understand that our Milky Way is just one of hundreds of billions of galaxies observable with modern telescopes. Each of these galaxies contains a staggering number of stars, typically around 100 billion. We inhabit one immense galaxy, spanning 100,000 light-years across and rotating gradually. Our Sun, a commonplace yellow star of average size, is positioned near the inner edge of one of these spiral arms, completing its orbital cycle every few hundred million years. Our contemporary understanding of the cosmos has progressed remarkably since the times of early scholars like Aristotle and Ptolemy, which we discuss in episode 1. In their time, the predominant belief positioned the Earth at the center of the universe, a perspective that has changed substantially over time as we have advanced our understanding of the extensive cosmic landscape. Stars, being incredibly distant, often appear to us as mere points of light, making it challenging to discern their size or shape. However, despite these limitations, astronomers can differentiate between various types of stars primarily by examining the color of their light. This breakthrough in understanding the nature of light and color came with Sir Isaac Newton's discovery. He found that when sunlight passes through a prism, a triangular-shaped piece of glass, it disperses into its constituent colors, creating a spectrum akin to a rainbow. Applying a similar principle, astronomers use telescopes to focus on individual stars or galaxies, allowing them to observe the spectrum of light emitted by these celestial bodies. Different stars exhibit distinct spectra, but the relative brightness of the various colors conforms precisely to the expectations for an object that is intensely hot and glowing, much like a red-hot object. Remarkably, the light emitted by any opaque object that is heated to a red-hot state possesses a characteristic spectrum determined solely by its temperature, a phenomenon known as a thermal spectrum. This implies that by analyzing the spectrum of a star's light, astronomers can determine its temperature. Moreover, during spectral analysis, astronomers observe specific colors that are absent or missing from a star's spectrum. These missing colors, known as absorption lines, provide additional information. The particular patterns of these lines may vary from star to star, offering insights into the star's composition and atmospheric conditions. Scientists can identify the chemical elements in stars' atmospheres by studying their light. Each element absorbs a distinct set of colors, creating dark gaps in the light spectrum. Astronomers match these gaps to known elements, allowing them to determine the composition. This study of the spectrum plays a crucial role in unraveling the characteristics and nature of stars. In the 1920s, with improved telescopes, scientists could analyze starlight not only within our Milky Way galaxy, but also from distant galaxies. Intriguingly, they discovered that the elements were consistent. The chemical fingerprints matched those of stars we were familiar with. However, the entire spectrum of distant stars was shifted towards the red end. It was as if some force had stretched out all the wavelengths of light towards the redder part of the spectrum. Baffled by this phenomenon, scientists realized the shift must be due to relative motion through the Doppler effect. The Doppler effect was first described by Christian Doppler. It is the change in frequency or wavelength of a wave in relation to an observer moving relative to its source. Just like how an ambulance siren changes pitch as it passes by. Light waves can be compressed or stretched out by motion. They theorized that distant galaxies must be moving away from us, causing the redshift as light waves get pulled to longer wavelengths. This revelation was monumental. It provided the first observational evidence that the universe is expanding over cosmic time scales. However, the surprising revelation came when Hubble published his findings in 1929. Contrary to expectations, he discovered that the majority of galaxies appeared redshifted, indicating that they were, in fact, moving away from us. What added to the astonishment was the observation that the extent of a galaxy's redshift is not random. Instead, it is directly proportional to the galaxy's distance from us. In simpler terms, the farther a galaxy is, the faster it is moving away. This groundbreaking observation led to a profound realization: the universe is not static, as previously believed, but is actively expanding. The distances between different galaxies are changing continuously. The recognition that the universe is in a state of expansion marked one of the great intellectual revolutions of the 20th century. Looking back, it might seem straightforward, but the concept of an expanding universe was a paradigm shift that reshaped our understanding of the cosmos. It sparked new avenues of inquiry and fundamentally altered the way we perceive the vastness and dynamism of the universe. The notion that a static universe, governed by gravity, would eventually start contracting was a reasonable expectation held by early thinkers like Newton. However, if we consider an alternative scenario where the universe is expanding, different outcomes emerge based on the rate of expansion. If the universe is expanding at a relatively slow pace, the force of gravity could potentially counteract the expansion, causing it to eventually slow down, stop, and then reverse into a contraction known as a big crunch. On the other hand, if the expansion rate exceeds a critical threshold, gravity would never be potent enough to halt it. In this case, the universe would continue expanding indefinitely, leading to a big freeze or heat death. The possibility of a big crunch is less favored in many contemporary cosmological models. The possibility of a big freeze and heat death is more widely considered. This behavior is analogous to launching a rocket from the Earth's surface. If the rocket attains a modest speed, gravity will eventually bring it to a stop, causing it to fall back to Earth. However, if the rocket surpasses a critical speed, approximately 7 miles per second, gravity becomes insufficient to pull it back, leading the rocket to escape Earth's gravitational pull and continue moving away. Remarkably, this understanding of the universe's potential fate, based on its expansion rate, could have been deduced from Newton's theory of gravity as far back as the late 17th century. Despite this, the belief in a static universe persisted well into the early 20th century. Even Einstein, when formulating the general theory of relativity in 1915, was so entrenched in the idea of a static universe that he introduced a modification known as the cosmological constant into his equations to make a static universe feasible. This constant represented an anti-gravity force inherent in the fabric of space-time, countering the attractive force of matter and maintaining a static state. Einstein proposed that space-time had an inherent tendency to expand, and this could precisely balance the gravitational attraction of all the matter in the universe, ensuring a static state. However, Alexander Friedmann, a Russian physicist and mathematician, was the exception. Instead of seeking ways to avoid the prediction of a non-static universe, as many physicists were doing, Friedmann embraced the implications of general relativity and worked on explaining and understanding them. Alexander Friedmann's groundbreaking contributions to cosmology were based on two simple yet profound assumptions about the universe. His first assumption asserts universal symmetry, stating that the characteristics of the universe appear the same in every observed direction, regardless of our vantage point. The second assumption builds on the first, proposing that this observed symmetry holds universally, emphasizing consistency regardless of an observer's location within the cosmos. These straightforward assumptions paved the way for significant insights into the dynamic nature of the cosmos. By contemplating these ideas, Friedmann reached a remarkable conclusion. A static universe should not be the expected outcome. In fact, as early as 1922, several years before Edwin Hubble's groundbreaking discovery, Friedmann made a prediction that aligns precisely with what Hubble would later find. Friedmann's work was instrumental in anticipating the observational evidence for an expanding universe. The assumption that the universe appears the same in every direction is an idealization that does not hold true in reality. A clear example is the distinct band of light formed by the other stars in our galaxy, known as the Milky Way, which stretches across the night sky. However, when observing distant galaxies, there appears to be a more or less uniform distribution of them. In essence, the universe seems to exhibit a rough uniformity in every direction, particularly when viewed on a large scale compared to the vast distances between galaxies. This perspective overlooks the variations on smaller scales. For a considerable period, this approximation served as sufficient justification for Friedmann's assumption, offering a rough approximation to the true nature of the universe. However, in a fortuitous turn of events, it was discovered that Friedmann's assumption is remarkably accurate in describing our universe. Despite the observable variations, on a grand scale, especially when considering the vast distances between galaxies, Friedmann's assumption aligns remarkably well with the actual structure of our universe. This realization emphasizes the power of theoretical insights and assumptions in providing accurate approximations and models for understanding the cosmos. In 1965, Arnaud Penzias and Robert Wilson were conducting tests on an exceptionally sensitive microwave detector. Microwaves, similar to light waves but with a wavelength of around a centimeter, were the focus of their investigation. However, the researchers were perplexed when they observed more noise than anticipated, and this noise did not seem to originate from any specific direction. Initially, they explored potential issues such as bird droppings and other malfunctions in their detector, but ruled these out. They realized that if the noise originated within the Earth's atmosphere, it would be stronger when the detector wasn't pointing directly upward due to the greater distance light travels through the atmosphere at lower angles. However, the excess noise remained constant regardless of the detector's direction, indicating an extraterrestrial source. The noise persisted day and night throughout the year, unaffected by the Earth's rotation and orbit around the Sun. This led them to conclude that the radiation causing the noise must come from beyond the solar system, and even beyond the galaxy. The consistent nature of the noise in all directions suggested that the universe, at least on a large scale, is uniform. They later realized that this noise was the same in all directions and had a temperature of about 3.5 Kelvin, which matched the predictions of the Big Bang theory. This accidental discovery served as a remarkably accurate confirmation of Friedmann's first assumption about the isotropy of the universe. The cosmic microwave background radiation, CMBR, is considered one of the most important pieces of evidence for the origin and evolution of the universe, as it provides information about how matter and radiation interacted in the early stages of cosmic history. Around the same time Penzias and Wilson were investigating noise in their detector, physicists Bob Dick and Jim Peebles at Princeton University were exploring microwaves. They were considering George Gamow's suggestion that the early universe was extremely hot and dense, emitting white-hot light. Dick and Peebles proposed that we should still be able to detect the glow of the early universe, now appearing as microwave radiation due to the redshift caused by the expansion of the universe. While Dick and Peebles were preparing to search for this radiation, Penzias and Wilson, unaware of their work, realized that they had inadvertently discovered it. In recognition of their contribution, Penzias and Wilson were awarded the Nobel Prize in 1978. The observation that the universe appears uniform in every direction might initially suggest that there is something special about our position within the cosmos. It could lead to the idea that, since we observe all other galaxies moving away from us, we must be located at the center of the universe. However, an alternative explanation exists. The universe might exhibit uniformity from the perspective of any other galaxy as well. This alternative is consistent with Friedmann's second assumption. Crucially, there is currently no scientific evidence either supporting or refuting this second assumption. Acceptance of this idea is driven by a sense of modesty. It would be quite extraordinary if the universe looked the same in every direction around us, but not around other points in the universe. In Friedmann's model, all galaxies are moving directly away from each other, akin to spots painted on an expanding balloon. As the balloon inflates, the distance between any two spots increases, but there is no single spot that can be identified as the center of the expansion. Moreover, the farther apart the spots are, the faster they will be moving apart. This analogy illustrates the concept that the universe's expansion does not necessitate a central point. Rather, all points that are galaxies are moving away from one another as the universe undergoes its dynamic evolution. In Friedmann's model, the velocity at which any two galaxies move apart is directly proportional to the distance between them. This prediction aligns with Hubble's observation that the redshift of a galaxy is indeed directly proportional to its distance from us. Despite the success of Friedmann's model and its ability to anticipate Hubble's findings, Friedmann's work remained relatively unknown in the Western scientific community until 1935. In that year, American physicist Howard Robertson and British mathematician Arthur Walker independently discovered similar models. Their work emerged in response to Hubble's revelation of the uniform expansion of the universe. It's noteworthy that, although Friedmann found only one type of model, there are, in fact, three distinct kinds that adhere to his two fundamental assumptions. The first kind, the type discovered by Friedmann, describes a universe expanding at a rate slow enough that gravitational attraction between different galaxies counteracts the expansion, eventually causing it to decelerate and come to a halt. This is often referred to as a closed universe. The figure on the above screen illustrates how the distance between two neighboring galaxies changes over time in the first kind of solution. The distance starts at 0, increases to a maximum, and then decreases back to 0. This pattern represents a universe that expands, slows down due to gravitational attraction, comes to a stop, and eventually contracts. In the second kind of solution, as depicted in figure, the universe is expanding at such a rapid rate that gravitational attraction cannot halt it completely, although it does exert some decelerating influence. This is often referred to as an open universe. In this scenario, the separation between neighboring galaxies starts at 0, and over time, the galaxies steadily move apart at a consistent speed. Lastly, there is a third kind of solution, where the universe is expanding just fast enough to prevent a collapse. This is often referred to as a flat universe. In the third kind of solution, the separation between neighboring galaxies also begins at 0 and increases indefinitely. However, the speed at which the galaxies move apart gradually diminishes, although it never quite reaches 0. This scenario implies an expanding universe where the galaxies continue to drift apart, but the rate of expansion progressively slows down. A notable characteristic of the first kind of Friedmann model, which describes a universe that expands, slows down, comes to a stop, and contracts, is that it presents a universe that is not infinite in space. However, it also lacks a boundary. In this model, gravity is so potent that it bends space back onto itself, resembling the surface of the Earth in a way. Just as one can travel in a certain direction on Earth's surface without encountering an insurmountable barrier or falling over the edge, in the first kind of Friedmann model, one would eventually return to the starting point without encountering spatial boundaries. This concept reflects the curvature of space under the influence of strong gravitational forces. In the first kind of Friedmann model, space behaves analogously to the surface of the Earth, but with 3 dimensions instead of 2. The fourth dimension, time, is also finite in extent, akin to a line with 2 ends or boundaries, a beginning and an end. It's important to note that this model predates the consideration of quantum mechanics and general relativity combined. As we delve into the combination of general relativity and the uncertainty principle of quantum mechanics, we'll discover that it becomes conceivable for both space and time to be finite without possessing any edges or boundaries. This theoretical framework allows for a more nuanced understanding of the structure of the universe. While the notion of circumnavigating the universe and returning to the starting point is intriguing in science fiction, it holds limited practical significance. The mathematical models indicate that the universe would recollapse to 0 size before one could complete such a journey. Achieving speeds faster than light would be necessary to return to the starting point before the universe's eventual collapse, a feat not permitted by the laws of physics as we currently understand them. In the first kind of Friedmann model, where the universe expands and recollapses, space exhibits a curvature similar to the surface of the Earth, leading to a finite extent. The space is bent in on itself, resulting in a closed geometry. In the second kind of model, where the universe expands indefinitely, space is bent the other way, resembling the surface of a saddle. In this case, space is infinite. Finally, in the third kind of Friedmann model, characterized by the critical rate of expansion, space is flat, also implying infinity. Determining which Friedmann model accurately describes our universe hinges on understanding its eventual fate, whether it will stop expanding and contract or continue expanding indefinitely. This determination relies on knowledge of the present rate of expansion and the present average density of the universe. If the density is less than a critical value, dictated by the rate of expansion, gravitational forces will be too weak to halt the expansion. On the other hand, if the density surpasses the critical value, gravity will eventually overpower the expansion, leading to a future recollapse of the universe. This interplay between expansion and gravitational forces forms the basis for predicting the ultimate destiny of the cosmos. Determining the present rate of expansion involves measuring the velocities at which other galaxies are moving away from us, utilizing the Doppler effect. This measurement can be carried out with high accuracy. However, the challenge lies in our less precise knowledge of the distances to these galaxies, as we can only measure them indirectly. Currently, we understand that the universe is expanding at a rate between 5% and 10% every billion years. Nevertheless, our uncertainty about the present average density of the universe is even more significant. When we tally up the masses of all the observable stars in our galaxy and other galaxies, the sum falls short by less than 1/100th of the amount required to halt the expansion of the universe, even considering the lowest estimate of the rate of expansion. It is crucial to note that our galaxy and others likely contain a substantial amount of dark matter, which eludes direct observation. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation, but only with gravity. Scientists have inferred its existence from observing the gravitational effects it has on visible matter, such as stars and galaxies. Dark matter makes up about 27% of the total mass energy content of the universe, while ordinary matter, the stuff we can see, makes up only about 5%. The rest is dark energy, a mysterious force that causes the expansion of the universe to accelerate. Dark energy is a property of space itself that exerts a repulsive force on all forms of matter and energy. Additionally, in the vast clusters where most galaxies are located, we observe the influence of dark matter in the spaces between galaxies, affecting their motion. Even when considering this contribution of dark matter, the cumulative effect remains only about 1/10 of the amount necessary to counteract the expansion. However, there's a possibility that another form of matter, uniformly distributed throughout the universe and yet undetected, might exist. This hypothetical matter could potentially raise the average density of the universe to the critical value required to halt the expansion. Presently, the evidence leans towards the likelihood that the universe will continue to expand indefinitely. However, what we can affirm is that even if a recollapse is in the universe's future, it wouldn't happen for at least another 10 billion years. This extended time scale should not overly concern us, as by then, unless humanity has ventured beyond the solar system, our species will likely have ceased to exist, along with our sun. This distant future is far beyond the scope of human existence as we currently understand it. All Friedmann solutions share a common feature. At some point in the past, roughly between 10 and 20 billion years ago, the distance between neighboring galaxies would have been zero. This moment, referred to as the Big Bang, signifies a time when the density of the universe and the curvature of space-time reached infinity. However, because mathematics struggles with infinite numbers, this implies that the general theory of relativity, upon which Friedmann's solutions are built, foresees a point in the universe where the theory itself becomes unreliable. Such a point is known as a singularity in mathematical terms. In practical terms, this singularity at the Big Bang challenges our current scientific theories, which assume that space-time is smooth and nearly flat. As a result, these theories break down at the Big Bang singularity, where the curvature of space-time becomes infinite. Consequently, even if events occurred before the Big Bang, they wouldn't provide a basis for predicting what would happen afterward. The predictability of events breaks down precisely at the Big Bang, creating a limitation in our ability to understand the nature of the universe at that specific point in time. Indeed, given that our knowledge is limited to what has transpired since the Big Bang, we face a fundamental challenge in determining events that occurred before this cosmic event. From our perspective, events preceding the Big Bang have no discernible consequences or impact on the observable universe. Consequently, these events should not be integrated into a scientific model of the universe. Therefore, a logical approach is to exclude them from the model and assert that time itself had a commencement at the moment of the Big Bang. This conceptualization acknowledges the limitations of our understanding and frames the beginning of time within the context of this pivotal cosmic event. One notable proposal was the steady-state theory, introduced in 1948 by Hermann Bondi and Thomas Gold, along with British scientist Fred Hoyle. These scientists, who collaborated on radar development during World War II, suggested that as galaxies moved apart, new galaxies continuously formed in the gaps between them from newly created matter. According to this theory, the universe would maintain a similar appearance at all times and locations. Although the steady-state theory required a modification of general relativity to account for the ongoing creation of matter, the rate involved, about 1 particle per cubic kilometer per year, did not conflict with experimental observations. The theory was considered scientifically sound, meeting the criteria of simplicity and making testable predictions. One such prediction of the steady-state theory was that the number of galaxies or similar objects in any given volume of space should remain constant throughout the universe. The steady-state theory faced a significant challenge when a survey of radio wave sources from outer space, led by astronomers at Cambridge in the late 1950s and early 1960s, revealed unexpected results. The researchers interpreted weaker sources as more distant and stronger sources as closer, noticing a lower density of common sources per unit volume for nearby sources compared to distant ones. This observation suggested either that we are situated at the center of a region where sources are fewer than elsewhere, or that sources were more abundant in the past at the time the radio waves commenced their journey to us. Both explanations contradicted the predictions of the steady-state theory. Additionally, the discovery of microwave radiation by Penzias and Wilson in 1965 provided further evidence that the universe must have been much denser in the past. These findings collectively led to the abandonment of the steady-state theory, as it could not account for the observed distribution of radio wave sources and the increased density implied by the microwave radiation discovery. In 1963, Russian scientists Sevgeny Lifshitz and Isaac Kalatnikov proposed an alternative explanation to avoid the idea of a Big Bang and the implied beginning of time. They suggested that the singularity at the Big Bang might be a specific feature of Friedmann's models, which are approximations to the real universe. According to their proposal, among all the models that resemble the actual universe, only Friedmann's might contain a singularity. Their argument rested on the distinction between Friedmann's models, where galaxies are depicted as moving directly away from each other, leading to a past moment when they were all at the same place, the Big Bang singularity. However, in the real universe, galaxies not only move away from each other, but also possess small sideways velocities. Lifshitz and Kalatnikov proposed that, in reality, galaxies need not have been precisely at the same place in the past, only very close together. This suggestion aimed to challenge the universality of the Big Bang singularity across all possible models of the universe. Lifshitz and Kalatnikov initially suggested that the present expanding universe might have resulted not from a Big Bang singularity, but from an earlier contracting phase. In this scenario, as the universe collapsed, particles within it might not have all collided, but instead flown past each other and then away, leading to the current expansion. They proposed models that were similar to Friedmann's, but accounted for irregularities and random velocities of galaxies in the real universe. Initially, they claimed that these models could start with a Big Bang, even though galaxies were not always moving directly away from each other. However, they later acknowledged that this was only possible in certain exceptional models where galaxies moved in specific ways. They argued that, since there appeared to be infinitely more Friedmann-like models without a Big Bang singularity than with one, there might not have been a real Big Bang. However, they withdrew this claim in 1970 when they realized that there was a more general class of Friedmann-like models with singularities, and that galaxies did not need to move in any special way. While Lifshitz and Kalatnikov's work demonstrated that the universe could have had a singularity, a Big Bang, if general relativity was correct, it did not definitively answer the crucial question: does general relativity predict that our universe should have had a Big Bang, implying a beginning of time? Roger Penrose's approach, introduced in 1965, provided an answer to the question of whether general relativity predicts the beginning of time. Using the behavior of light cones in general relativity and the fact that gravity is always attractive, Penrose demonstrated that a star collapsing under its own gravity becomes trapped in a region whose surface eventually shrinks to zero size. As the surface shrinks to zero, the volume of the region also approaches zero. This compression results in all the matter in the star being squeezed into a region of zero volume, leading to the density of matter and a curvature of space-time becoming infinite. This scenario describes a singularity contained within a region of space-time known as a black hole. In essence, Penrose's work implied that the collapse of a massive star could lead to a singularity, akin to the central concept of a black hole. This conclusion had profound implications for the nature of singularities in the context of general relativity. At the time Stephen Hawking encountered Roger Penrose's theorem, he was a research student facing a diagnosis of amyotrophic lateral sclerosis, commonly known as motor neuron disease. Given a prognosis of only 1 or 2 more years to live, Hawking initially saw little point in pursuing his PhD thesis. However, as time passed and his condition did not deteriorate as rapidly as expected, Hawking found himself in a different situation. Engaged with Jane Wilde and facing the practicalities of marriage, he recognized the need for a job, which in turn required completing his PhD. This personal backdrop underscores the determination and resilience that Hawking displayed in his academic pursuits despite facing significant health challenges. This glimpse into Hawking's personal life also serves as a reminder of the human stories behind scientific breakthroughs and the perseverance of individuals in the face of adversity. Stephen Hawking's realization and application of Roger Penrose's theorem in 1965 marked a crucial moment in cosmology. Penrose's original theorem focused on the gravitational collapse of massive bodies leading to singularities, particularly within the context of black holes. Hawking, in a stroke of insight, recognized that by reversing the direction of time in Penrose's theorem and considering the conditions of his own time, one could infer that any expanding universe resembling a Friedmann model must have originated from a singularity. This insight, often referred to as the singularity theorems, played a significant role in shaping our understanding of the origin of the universe. In essence, Hawking demonstrated that if the universe is expanding and follows certain conditions, then it must have had a beginning, a singularity. However, it's important to note that these theorems don't provide detailed information about what happened at the exact moment of the singularity or what conditions prevailed then. The joint paper by Roger Penrose and Stephen Hawking in 1970 represented a significant advancement in the understanding of singularities in the context of general relativity. By removing certain technical conditions, they established that, under the assumptions of general relativity and the presence of observed amounts of matter, a Big Bang singularity was inevitable. This work, commonly known as the singularity theorems, contributed to the widespread acceptance of the idea that the universe originated from a singularity, a concept integral to the Big Bang theory. It's noteworthy that the acceptance of these theorems faced some opposition, including from those who found the idea of singularities distasteful or believed it conflicted with the elegance of Einstein's theory. The mathematical rigor of the theorems ultimately prevailed, and the concept of a singularity at the beginning of the universe became a standard part of cosmological understanding. The discovery of the universe's expansion, coupled with the awareness of Earth's insignificance in the vast cosmic expanse, marked the beginning of this transformative journey. The realization that the universe must have had a beginning in time culminated in the 1970 proof by Roger Penrose and Stephen Hawking, based on Einstein's general theory of relativity. Hawking acknowledges that while general relativity provides insights, it is an incomplete theory unable to explain the universe's origin. The singularity theorems demonstrated that at the universe's early stages, the breakdown of physical theories, including general relativity, necessitates considering the effects of quantum mechanics. This realization prompted a shift from exploring the universe on an extraordinary scale to delving into the realm of the extraordinarily tiny quantum mechanics, which I discussed in our video, The Heisenberg Limit. Link is in the description below. In 1998, two teams of astronomers observed distant supernovae and found that they were moving away from us faster than expected. This implied that the universe was expanding faster than the speed of light, which contradicted Einstein's theory of relativity. Since then, many other observations have supported the existence of dark energy, such as the cosmic microwave background radiation, the large-scale structure of galaxies, and the gravitational lensing effect. The video's conclusion posits that the expansion of the universe can be attributed to the Big Bang, and that its acceleration is driven by the influence of dark energy. The Big Bang theory suggests that the universe began as a singularity and has been expanding ever since. This theory is supported by various observations such as the cosmic microwave background radiation and the redshift of distant galaxies, which indicate they are moving away from us. The discovery that the universe's expansion is accelerating was indeed surprising. This acceleration can't be explained by known matter or energy, leading scientists to propose the existence of dark energy. Dark energy is a mysterious form of energy that permeates all of space and is believed to be the force driving the acceleration of the universe's expansion. While we have made significant strides in understanding these cosmic phenomena, there is still much to learn about the exact nature of dark energy and its implications for the future of the universe.